In this video, we'll be looking at section 8.1, which covers the law of sines. So the law of sines is a way that's going to help us solve triangles. So if we are given a triangle with angles and sides opposite labeled as shown, the ratio of the sine of the angle to the length of the opposite side will always be equal. So you'll see we have a triangle here with side lengths A, B, and C. And then we have the opposite angles from those sides labeled. So with this in mind, the sine of angle alpha over side A, which is opposite from it, is equal to the sine of angle beta over side B, which is opposite from it, which is equal to the sine of gamma over C, which is the side opposite of it. So like I kind of mentioned here, for clarity's sake, we call side A the corresponding side of angle alpha because they're opposite of each other, so we say it corresponds to each other. Similarly, we call angle alpha the corresponding angle of side A. And then we use the same idea for side B with angle beta, as well as side C and angle gamma. So we're going to start off by solving two triangles that use the straightforward case of law of sines. We'll see in the next examples that it's not always that clear. So since we're solving triangles, make sure that your calculator is in degree mode, because when we're working with triangles, we don't do radians. That's just not a thing. So first up, we have a triangle here with two angles marked and a side. Well, we can find the third angle for sure, because the three angles of a triangle add up to 180. So if I take 180, subtract 40, and subtract 110, that leaves us with 30 degrees. So that's going to be that angle there. Now we're going to use the law of sines to help us find the other two sides. We can't use the Pythagorean theorem because the Pythagorean theorem only works if we have a right triangle. This one's not a right triangle, so we're going to have to use this law of sines. So if I set up the full equation, we will have the sine of 110 degrees over the opposite side, 18, is equal to the sine of 30 degrees over its opposite side, I'll call it x, which is going to be equal to the sine of 40 degrees over its opposite side, which I'll call y. So now I'm just going to take different parts of this equation and work with them. So first up, I'm going to ignore this third part, and we have the sine of 110 degrees over 18 is equal to sine of 30 degrees over x. I'm going to cross multiply. So I'll have 18, wrong marker. I'll have 18 times the sine of 30 degrees is equal to x times the sine of 110 degrees. If I divide both sides by the sine of 110, we get that x is equal to 18 times the sine of 30 over the sine of 110. I'm going to go ahead and type that in. My calculator is already in degree mode, so I'll have 18 sine of 30 divided by the sine of 110 is equal to 9.5776 if I round to 4 decimal places. 9.5776. Now I'm going to use the first one and the last one because those numbers are easy to work with. And I'm going to cross multiply with that. So I'll have y times the sine of 110 is equal to 18 times the sine of 40. If I divide both sides by the sine of 110, I get y is equal to 18 times the sine of 40 over the sine of 110. And 18 times the sine of 40 divided by the sine of 110 is equal to 12.3127. So I've now solved for all three angles and all three sides. I'm done. Let's try this next one. We have two angles and a side. So we have 45 degrees, 75 degrees, and 15. I can solve for my third angle if I take 180 degrees and I subtract 45 and the 75. That's going to give me 60. That angle is 60 degrees. If I set up my law of sines, then the sine of 60 degrees over its opposite side, 15, is equal to the sine of 45 degrees over its opposite side, which I'll call x over here. And I'll just go over here because I don't have room. It's equal to the sine of 75 degrees over its opposite side, which I'll call y. Now I'm just going to do my cross multiplication. I'll solve for x first. So I'll have x times the sine of 60 is equal to 15 times the sine of 45. Dividing both sides by the sine of 60, I get x is equal to 15 times the sine of 45 over the sine of 60. If I type that in, that's going to be 15 sine of 45 over the sine of 60. That gives me 12.2474. And then if I cross multiply solving for y, I'm going to have y times the sine of 60 is equal to 15 times the sine of 75. Solving for y, I divide both sides by the sine of 60, and we get y is equal to 15 times the sine of 75 degrees over the sine of 60 degrees. Which gives me 16.7303. And I've solved for that triangle. So this law of sines is helping us solve for the sides of a triangle because we can find the angle, we just need to find the sides. But there are some other cases where we can use the law of sines, but things get just a little bit funkier. And it's called the ambiguous case for the law of sines. If we know two side lengths and a non-included angle, we may find two, one, or no triangles that satisfy the given information. So we're going to solve the following triangles for the unknown sides and angles if possible. If there's more than one possible solution, we're going to get both. We're going to assume that angle alpha is opposite side A, beta is opposite side B, and gamma is opposite side C. I'm going to use a blank piece of paper so that I have some space to work with here. I'm going to draw just a generic triangle. We will say we have A, B, and C. So this is alpha, beta, and gamma. So first up, we know the angle alpha is 119 degrees. We know A is 26, and we know B is 14. So let's start with that. So in this case, I can't solve for another angle right away because I only have one of them. So I need to use what I do have, see what I can find. So I'm just going to set up my law of sines, the whole thing, and we'll see what I can do. So the sine of angle alpha, which is 119 degrees, over A, which is 26, is equal to the sine of angle beta, which I don't know yet, over side B, which is 14, is equal to the sine of angle gamma over side C, and I don't know that yet either. What I can see with this is If I look at the first two expressions, the sine of 119 over 26 and the sine of beta over 14, I can cross multiply those because the only unknown I have there is beta. So if I cross multiply this, then I have 14 times the sine of 119 degrees is equal to 26 times the sine of angle beta. I can divide both sides by 26, and we get the sine of angle beta is equal to 14 times the sine of 119 over 26. So now I'm going to inverse sine both sides. So if I take the inverse sine of 14 sine of 119, and divide that by 26, I get the angle beta is 28.0959 degrees. But remember, sine is positive in quadrant 1 and quadrant 2. So it's also possible that beta is equal to 180 minus this, which means beta could also be equal to 151.9041 degrees. This is why it's called the ambiguous case. It's possible we have two different values for beta. Hopefully you're seeing a problem with this though. The three angles of a triangle have to add up to 180 degrees. If alpha is already 119 degrees, beta can't be 151 because that pushes us over 180 degrees. So this isn't actually possible, but this one still is. So if we now know beta is equal to 28.0959, we can solve for angle gamma. Gamma is going to be equal to 180 degrees minus the 119 minus the 28.0959. And if we take 180 minus 119 minus 28.0959, we get the angle gamma is 32.9041 degrees. Now that we know what gamma is, and that's a terrible gamma. Now that we know what gamma is, we can use this first term and the last term and set them equal, and we can cross multiply. So we get c times the sine of 119 is equal to 26 times the sine of gamma, but we just found gamma. So that's going to be the sine of 32.9041. Dividing both sides by the sine of 119, we get c is equal to 26 times the sine of 32.9041 all over the sine of 119. 26 times the sine of 32.9041 divided by the sine of 119. It looks like c is equal to 16.1488. So we solved for angle beta, angle gamma, and side c. We found the three unknowns. Let's try the next one. So in this next one, we are told angle beta is equal to 50 degrees. Side A is equal to 105, and side B is equal to 45. So as a reminder of something I said before, we can't just use the Pythagorean theorem because that only works with right triangles, and we don't know we have a right triangle, so we have to use this law of sines to help us out. I'm going to go ahead and set up my equation with the law of sines. So we have the sine of angle alpha over side A, which is 105, is equal to the sine of beta, which is 50 degrees, over side B, which is 45, is equal to the sine of angle gamma over C, and we don't know either of those. If I use the first two, I only have one unknown, that's alpha, so I will cross multiply to help me find alpha. We're going to get 45 times the sine of alpha is equal to 105 times the sine of 50 degrees. Dividing both sides by 45, we get the sine of alpha is equal to 105 sine of 50 degrees over 45. 105 sine of 50 divided by 45. I inverse sine that. Domain error. Wait, let's go look at that again. Well, I can't see it. Let's solve for it again. 105 sine of 50 over 45. And I have to inverse sine that? Wait a minute. Sine can't be 1.787. Sine has to be between -1 and +1. This is the case where there is no triangle. There's no solution. It is impossible to have a triangle that has an angle beta of 50 degrees, side B of 45, and side A of 105. That just can't happen. So let's try the third one now. We're told that angle alpha is equal to 43.1 degrees. Side A is 184.2, and side B is 242.8. I'll go ahead and set up my law of sines equation. The sine of 43.1 degrees over 184.2 is equal to the sine of beta over what B is, 242.8, is equal to the sine of gamma over C. If I use the first two, then I only have one unknown. It's going to be beta. So I'm going to use this first equals to help me solve for beta. Cross multiplying, I'm going to have 242.8 times the sine of 43.1 is equal to 184.2 sine of beta. I can solve for sine if I divide both sides by 184.2. That'll give me the sine of beta is equal to 242.8 sine of 43.1 degrees over the 184.2. So 242.8 sine of 43.1 divided by 184.2, and then inverse sine that, and we get that beta is equal to 64.2430. But like we said before, sine is positive in quadrant 1 and quadrant 2, so let's see what this would be in quadrant 2. If I take 180 and subtract that, that would be my quadrant 2 answer. So beta could also be equal to 115.7570, and those are in degrees. Alpha is 43.1 degrees. I could use either one of these because the three angles have to add up to 180. Neither of these, when added to alpha, puts me over that 180 degrees. So this is going to be a case where I have two different triangles. I'm going to use this first one. I'm going to call it beta 1. In the second one, I'll call beta 2, so that I know I'm working with two separate triangles. So we're going to work with triangle 1 first, and then we'll come back and attack triangle 2. So in triangle 1, we already know what beta is. We'll be able to solve for gamma because gamma will be 180 minus the 43.1, which is alpha, minus the 64.2430 that we got for beta. 180 minus 43.1 minus 64.2430 tells us that angle gamma is 72.650 degrees. Now I'm going to use my first and third terms here and cross multiply. If I do that, I'll have C times the sine of 43.1 degrees is equal to 184.2 times the sine of gamma. But we know what gamma is. Gamma is a 72.6570. Sorry, running out of room. To solve for C, I divide both sides by the sine of 43.1. And we get C is equal to 184.2 sine of 72.6570 over the sine of 43.1. And 184.2 sine of 72.6570 divided by the sine of 43.1 tells me that C is equal to 257.3284. I should have noted this before. This is triangle 1. So we named angle beta, beta 1. So really, this is gamma 1 and C1. Because those are all just for the first possible triangle. There's another possible triangle out there that we need to find. So let's work with that one. For triangle 2, we already know what beta is. So our other choice for gamma, our gamma 2, will be 180 degrees minus what alpha is, minus what beta 2 is. And that gives us that gamma 2 is equal to 21.1430 degrees. I'm going to be able to solve for my second value of C by again using cross multiplication on my original law of sines. So I will have C times the sine of 43.1 is equal to 184.2 times the sine of gamma. But we just found gamma to be 21.1430. So to solve for C, and really it's C2, divide both sides by the sine of 43.1, and we get C2 is equal to 184.2 sine of 21.1430 all over the sine of 43.1. I'm getting C to be 97.2383. So again, this is a case where we have two different triangles because when we solved for the first angle, we had to remember that sine is positive in both quadrant 1 and quadrant 2. And both the quadrant 1 and quadrant 2 angles were possible in this case because with the angle we already had, alpha, it didn't push us over that 180 degree limit. So that gave us two separate triangles. This last thing we're going to look at in this section is solving these two triangles. So let's set up our law of sines. I'll call this, we'll say A, this one can be beta, this one can be gamma. So if I set up my law of sines, I'll have the sine of 30 degrees over A is equal to the sine of beta over 10 is equal to the sine of gamma over 16. But there's a problem here. If I use the first two, I have two unknowns, A and beta. If I use the last two, I have two unknowns, beta and gamma. If I use the first and the third, I have two unknowns, A and gamma. I can't solve this triangle using the law of sines. In fact, I'm not going to be able to solve this triangle either because in all three cases, I don't know any angles. So I'll always have the two angles as two unknowns. So the law of sines doesn't help us all the time. There are cases where we can't use the law of sines to solve. This is what leads us to the law of cosines, which we're going to look at in the next section.